The next theorem that we have is called the complex conjugate theorem. It says something kind of interesting. It says that if you have a complex number that's a zero of a polynomial, a plus bi, then the conjugate is also a zero, a minus bi. So that means our imaginary roots always happen in pairs. So let's use that. We have a function of degree 3. One of its zeros is -1, and another is 5i. Now 5i is imaginary, so that means it's going to have another zero of its conjugate. The conjugate of 5i is -5i. So we want to figure out what this function is. So remember, if -1 is a zero, that means x plus 1 is a factor. So it's the opposite. If 5i is a factor, that means x minus 5i is a factor. And if -5i is a zero, that means the opposite, x plus 5i is a factor. So knowing our 3 zeros gives us our 3 factors. And now all we need to do is multiply this out. Now, I'm not going to do anything with the x plus 1 yet, but I am going to FOIL these two. So that's going to give me x squared plus 5ix minus 5ix minus 25i squared. All right, so that's x squared. Those two are going to cancel out, and then we have -25 and I squared. Remember, I squared is -1, so this is -25 times -1, which is +25. And then I have x plus 1, and then I'm just going to finish multiplying these two things. So I get x cubed plus 25x plus x squared plus 25. And then if you just want to rearrange it, the function will be, we'll just call it f of x, is x cubed plus x squared plus 25x plus 25. Okay, let's try another one of these, just the same idea. So we want a polynomial function with degree 3 that has zeros, -1 and 1 plus 2i. So if our zeros are -1 and 1 plus 2i, that means the other zero is 1 minus 2i. So if these are our zeros, the factors come from the opposite, so x plus 1, and then x, both of these things have to be opposite, -1 minus 2i. And then both of these have to be opposite, x minus 1 plus 2i. Okay, so we need to multiply this out. So I'm not going to do anything with this yet. I am going to multiply the other two. I'm going to use the box method because that's kind of an ugly mess. So x minus 1 minus 2i across the top, x minus 1 plus 2i across the side. All right. So that's going to give us x squared minus x minus 2ix. And then minus x plus 1 plus 2i. And then 2ix minus 2i minus 4i squared. Okay, now the like terms are not quite on the diagonals, but we do have 2i and -2i and 2ix and -2ix. So this is going to be x squared, here's some like terms, minus 2x. And actually these are like terms because -4i squared, that's going to be +4, so plus 5. So this thing multiplies to this. And now we're going to multiply these next two things together. You can use box method again, which maybe I will. Just do box method one more time so we can get a nice neat answer. If you would rather FOIL them out, that is totally fine. So x squared minus 2x positive 5, And then we're going to have x and 1. Okay. So this will be x cubed minus 2x squared and positive 5x, x squared minus 2x and 5. So our final answer, I'll write it over here, is x cubed minus x squared plus 3x plus 5. All right, we're going to do just one more of these, okay? This next one's easier. So now we want a polynomial with degree 3. It's got zeros of 0 and 5. Neither of these are imaginary, so there's no partner with it. So one of our zeros is 0, so that's x minus 0. One of our zeros is 5, so that makes this factor x minus 5. So we can write that as x minus 5. But this is degree 3. It's supposed to be degree 3. The solution that I have is only degree 2. So that means I need to square one of these. It doesn't matter which one. So maybe I square that one. That would be an appropriate answer. Or you could square the other one. May say x minus 5 squared. Okay? Doesn't matter which one. And then you could FOIL those both out to get a final answer. Okay? So if you have degree 3 but not enough zeros, if you don't have 3 zeros, that means one of them has to be repeated. And it didn't tell you which one, so we just get to pick one.